In this video, I will show you how to derive the Stefan-Boltzmann law from thermodynamics without resorting to quantization of the energy. So we start from the energy momentum tensor T mu nu, and in particular we are going to rewrite it in the case of electromagnetic fields. We know that in this case we can rewrite this as 1 over 4 F alpha beta G mu nu minus F mu alpha F nu alpha, and this is written in natural units because otherwise there are other constants that multiply this energy momentum tensor, but that's not important. We can show that the trace of this tensor is 0, and the trace is T mu mu, written like this, which is equal to G mu nu T mu nu, and this is equal to, when I multiply G mu nu with upper indices with G mu nu with lower indices, I will get a factor of 4, which will cancel this factor of 1 over 4. So we are left with F alpha beta, and then here when I multiply by G mu nu with upper indices, I can rewrite this as minus F nu alpha, and I have to sum over nu and over alpha here, but this product can also be written as F nu alpha times F nu alpha like this, and therefore here you can see that we get 0. That's simple. Now for matter, we can also write the energy momentum tensor T mu nu. For matter, this can be written as T alpha beta with upper indices times G alpha mu, G beta nu, like this. And we know how to express T alpha beta with upper indices. T alpha beta with upper indices in the case of matter can be written as minus G alpha beta times pressure plus, here we have the energy density U plus P dx alpha ds dx beta ds. And let's take the trace of this tensor. In particular, we need G mu nu T mu nu, which you can easily find that this is equal to G alpha beta with lower indices times T alpha beta with upper indices. It's easy to show due to the properties of tensors, and this is equal to minus 4p plus u plus p, and then here when I multiply this by G alpha beta, we get ds squared over ds squared, which is 1. So here we multiply by 1, and this gives us u minus 3p. Now if we think of u as the radiation energy per unit volume, so this internal energy, this is the energy density, which can be thought of as the internal energy or the energy of radiation, whereas P, if we want to employ the definition of T alpha beta, not just for matter, but for the electromagnetic field, which can still be thought of as matter. And in this case, P represents the pressure due to radiation. So it's called the radiation pressure. But this definition here, or this definition here for the trace, should give us the same result, which is 0, and therefore this should be 0. So from here we get that radiation pressure is equal to the energy density of the electromagnetic field divided by 3. And now we know from thermodynamics that the differential of the internal energy contained in some volume, where in this case this letter U should not be confused with this letter U, so you have to think of this as uppercase U, whereas this should be thought of as lowercase u, and in particular the derivative of uppercase U with respect to the volume will give us the internal energy U per unit volume. So there is this link, this connection between the two. Now du is equal to the differential of heat, and in particular that's an inexact differential, so I could write it like this, d slash q, but d slash q is equal to T times the differential of the entropy. T is the temperature, and then here we have minus pressure times the differential of the volume. So if the volume decreases, it means that we have compression. Therefore, with this minus sign, it will become positive because dV is negative, and therefore this will give us a positive contribution for an increase in the internal energy. So that's quite intuitive. And now from this law here, you can see that the derivative of U with respect to volume at constant temperature is equal to temperature times the derivative of the entropy with respect to volume at constant temperature minus P, minus pressure. Now, what we can prove from simple thermodynamics is that ds over dv at constant temperature is equal to the derivative of pressure with respect to temperature at constant volume. So we can find that this is equal to this, and this is what we are going to do now. It's quite simple because this differential law can also be rewritten in this fashion. So we can rewrite this as the differential of capital U minus Ts, and from basic rules of calculus, this can be written as minus S dt minus P dV. But now, this function here is usually called F, and it represents the free energy. And as you can see here from these two differentials, dt and dv, this is a function of t and v. So from here, you see that minus s is equal to the derivative of f with respect to t at constant volume, and minus p is equal to the derivative of f with respect to v at constant temperature. But now, if you differentiate one more time this function with respect to volume, and you differentiate this function with respect to temperature, you should get the same thing, right? Because you get d squared f dv dt on both sides, and you can exchange the order of these derivatives. So from here, you see that minus the derivative of s with respect to volume at constant temperature is equal to minus the derivative of p with respect to temperature at constant volume. So we can cancel these two minus signs and we get plus. So we have proved this equation here, from which we can rewrite this equation like this. So on the left here, you see that we can replace that derivative with the lowercase u. So the energy density of radiation per unit volume. Then this is equal to T, and then we get derivative of P with respect to temperature at constant volume minus P. But now we also know that P is equal to U divided by 3. So we can replace this equation in the first one, and when we do that, we get U equal to T divided by 3 du dt at constant volume minus U over 3. We can multiply by 3, so we get 3u, and here we can get rid of this and this. And also, by the way, du dt at constant volume can also be written as a total derivative, du over dt, because the energy density per unit volume does not depend on the volume. It depends on temperature, but does not depend on the volume. So we can rewrite that equation as du over dt equal to 4u over t. And therefore, this can be rewritten as du over u equal to 4 dt over t, from which we can easily find that this is ln u, natural logarithm of u, equal to 4 times natural log of t plus some constant here, that I will not label. And if you exponentiate both sides, you get that u is equal to a constant times t to the fourth power, t to the fourth, like this. So as you can see, we found the proportionality between the temperature to the fourth power and the energy density of radiation, which is something that can be found in other ways by considering light being made of discrete units. And in that case, this constant here could be calculated. But as you can see from this method, it is not really possible to determine the value of this constant. You just get the proportionality between temperature to the fourth power and u.